Good afternoon. I am Kedar Rao. I'm in lab MO3 on Tuesdays from 12 to 3 p.m. This is lab 1, constant velocity motion. My observation is rolling a tennis ball, and there are two main assumptions in this lab. According to Newton's second law, there will be a net force of 0 because there is constant velocity. And we're also assuming that the model provides a good representation of motion. Here's my video. My roommate is rolling a tennis ball, and I'll just play it for you. I started the ball after the initial roll, and I set up the coordinate system so that, as you can see, it's pointing to the left. So the x-axis, the positive x-axis, is going to the left, and the ball is moving supposedly at a constant velocity. So the net force is 0. And I use the center of the ball as my initial position, and I use the diameter of the ball, which is 0.067 meters, as my calibration. The time frame for the video was 0.067 meters. Oh, sorry, was 0.08 seconds. And I ended the clip before the ball stopped. So the mass of the ball, and it was I looked it up, it was 0.057 kilograms. And to find the initial velocity, I had to find the change in initial position from the whole period, which is 0.678 minus 0.149 minus the total change in time, which is 0.8 minus 0. And I found that my initial velocity was 0.661 meters per second. I found my initial position by just looking at where I started the video, which is 0.149 meters per second. Now my delta t is 0.01 because it's smaller than my 0.08. I decided to go with that. Because velocity is constant, final velocity has to equal initial velocity. So for that to be, the net force, it has to be 0. So the formula really is just final velocity equals initial velocity, because F net divided by mass times delta t is just 0. So you can see that in my force vector, F net equals vector 0, 0, 0. Let's look at the visualization of the whole code. The ball moved towards the positive x axis and moved at a constant velocity. And you can see here on the graph that it starts from 0 and ends at 0.8, and it starts at 0.149 and ends up at 0.678. And it's moving at a constant slope, meaning a constant velocity. Graphed my points from the tracker, and this is the slope. The blue line is the slope that I got from my experiment. As you can see, it is very nearly exactly linear, which is a very good representation of what should actually happen. So for my what if question, they ask what if my motion was in the negative x direction. So if it was, as you can see here, I changed my vector, my x position to be a negative 0.149, and because it's moving in the negative direction, my velocity will also be negative, so I have it at negative 0.661. So let's just run the module. And you see here that it moves in the negative x-axis right here. The ball is moving towards the left, and that's going to be the negative axis. And you can see here that it starts at negative 0.149 and ends at negative 0.8. And it's moving in a negative direction, so it'll have a negative slope, meaning negative velocity. So what this is basically telling us is that if we didn't have a constant force acting on the ball, the velocity would not be constant. It would be it'd be changing. It would be increasing or decreasing. So that's just something to keep in mind. It would also it could also change direction. The velocity could also change direction. So let's test that. Let's see if if we make a different net force vector, what happens to the velocity of the ball. So you can see here that the slope is definitely not constant. The ball is moving at increasing speed, and you can see here by the curvature of the graph. And yeah, this just basically represents that a net force is not constant and is acting upon the ball. Yeah, that's it. Thank you for your time.